All right, next we are on to rotation. So it says calculate the net torque produced in the diagram at the right. So torque, so I have two things sitting on this beam, or like teeter-totter. So I'm going to call that FL plus an FL. I have two of them. All right, so this thing here creates a downward torque, but in terms of my pivot point, this thing kind of like makes the teeter-totter go down like this, like rotate down. And so it makes the teeter-totter go clockwise. So I'm going to call this a clockwise torque. So we have to remember that clockwise torques are negative. So I have to put a negative in. So this is negative 20. And L is called the torque arm. How far is this weight to the pivot point? So that's 0.5. Plus the 4, if I hold my finger on the pivot point, is going to make the teeter-totter go like this. It's going to make it rotate counterclockwise. So call this counterclockwise. And counterclockwise things are positive. So that is 4 times 0.25. And if I number crunch this, I'm going to get a negative, negative 0.9. Scribble that out. And the units would be Newton meters. Newton meters. That is the net torque. All right, the next question says a merry-go-round with a moment of inertia of 10 rotates about its center. What is the rotational kinetic energy? So what is the equation for rotational kinetic energy? 1/2 I W squared. And it's a merry-go-round, so the I is 1/2 mr squared. You don't need to know the I's. Somebody would always tell you the I's. So let's plug in our numbers. So 1/2. So, oh, I didn't even need that. Look at moment of inertia is 10. So the I value was 10. They just told it to me. And the angular velocity is 25 squared equals 3125 joules. All right, in this question, we are looking at conservation of energy when something is rolling without slipping instead of just sliding up or down a hill. So we have a wheel that is rolling without slipping along this horizontal surface, and it is going to go up the hill. And the question is how high up? Determine the height that it will reach. But we're doing the whole thing in variables, which actually makes the problem easier. So we're going to kind of talk to ourselves. So we really have three kinds of energy that we're talking about. We're talking about potential energy, kinetic energy, that means translational kinetic energy, and rotational kinetic energy. So when we are down here on the ground, we do not have any potential energy, but it is rolling without slipping. So that means we do have some translational kinetic energy. And we have the rolling kind of kinetic energy, which is 1/2 IW squared. And then it is going to go up the hill and get to the top. And when it gets to the top, it's not rolling anymore. It's not moving anymore. It just has potential energy. So I'm just going to set it equal to mgh. And now it's just understanding the variables and knowing how to solve for each. All right, so let's expand these a little bit. So we have 1/2 mv squared. And depending on what is rolling, the I often changes. So they told us what is rolling is this weird shaped wheel that has a weird I equation, or an unusual I equation. So I'm going to plug that in there. And I would like to get rid of that angular velocity. And we remember that V equals RW. which means the angular velocity would be equal to v over r. But since it's squared, it'll turn out to be v squared over r squared equals mgh. All right, let's do a little cleaning up. So I noticed that in every term I have an m. So I could cancel those m's. So the mass of it does not matter. And in this term, I have an r squared in the denominator, and I have an r squared in the numerator, so I can cancel those. All right, let's see what we got left. So we have 1/2 v squared plus, here we have 1 times 3v squared on top. And what do we get on the bottom? 2 times 7 is 14 equals just gh. All right, again, I'm solving for h. So let's look over here. We're adding something, but we need to have a common denominator. So I'm going to take this 1/2 and write it as 7/14. And we'll leave this one. So that's going to be 10v squared. 10v squared over 14 equals gh. We could reduce this fraction and turn that into 5/7. 5/7v squared equals gh. And again, we're solving for h. So I'm going to divide both sides by that g. Okay, this next question is about angular momentum. So we have an ice skater who's spinning with her arms in, and then she's going to move her arms out. And the question is, what is the resulting angular speed? So I have to know that when I move my arms in and out, that my speed will compensate for the changing rotational inertia. And that is because of conservation of momentum. So we have conservation of angular momentum when her arms are in has to equal the conservation of, or the angular momentum when her arms are out. So when her arms are in, we have IW. And when her arms are out, we have IW. And we're solving for this. So when her arms are in, her rotational inertia is 1/3 I. And she's spinning with angular speed W. But then she's going to pull her arms out, making her rotational inertia bigger. So that's going to be 3/4 I. And then the question is, what is the resulting angular speed? So we just have to solve for this new final velocity. So I have an I on both sides, so that can cancel. And then I have, this will be like W over 3. And this is going to be 3W over 4. But these W's are not the same because we're solving for this one. It's going to change. So to get this answer, I'm going to multiply both sides by 4. It's going to give me 4W over 3 equals 3W. Now I'm going to divide both by 3. And I get 4W over 9. So it's going to be, it is going to be, 4/9 of what it used to be. So next we are moving into the concept of fluids. So what is the approximate absolute pressure in the ball? So the absolute pressure is equal to the atmospheric pressure plus the gauge pressure. So our pressure gauge reads 4.6 psi. 4 4.6 psi. Atmospheric pressure is 101.325. But this is pascals and this is psi. So I'm going to convert psi into pascals. So I'm going to go into my pressure conversion menu, and we have 4.6 psi into this, and this turns out to be 31715.9 plus 101.325, and that is approximately 13304, rounded off 1 pascal. Okay, air flows from a wide section of a pipe into a narrow section. In which section of the pipe is the air pressure the greatest? So this is just knowing facts about how pressure changes due to velocity and what happens when the pipe narrows. So when the pipe narrows, the velocity increases. That's just a fact we're supposed to know. And if the velocity increases when the wind whips, the pressure dips. So pressure is going to be low in this area, which means the pressure in the wide section is going to be the greatest. All right, the next question talks about the drag force of a viscous fluid. This is not a main topic, but this is like the main topic the IB focuses on in terms of fluids. So we want to make sure that we have this down. All right, so when you put something such as a small bead in a graduated cylinder filled with honey, it's going to slowly fall through that honey. And it's going to accelerate initially, but it's very quickly going to reach terminal velocity. And when it reaches terminal velocity, which of these would be the free body diagram? So it's going to reach terminal velocity when the upward force equals the downward force. And so the downward force is going to be the weight. And the upward force is I'm going to have drag acting against me. So I'm going to have drag. But because I'm in a fluid, there's also a buoyant force that is acting upward. And the length of these two arrows summed together has to equal the length of the arrow going down. This one is bad because it doesn't take into account drag. This one has drag pointing the wrong way, and this one forgot about the buoyant force. So just remembering that you have both drag and a buoyant force when you fall through a viscous fluid. All right, when you have a drag force, we should know about the velocity and we should know about the acceleration in terms of their graphs. All right, so which of the following velocity time graphs, these are velocity time graphs, shows the velocity of the bead as it approaches terminal velocity? Well, when you first drop in the bead, it is going to be accelerating. So look at the slope of this line. There's the acceleration. And then here's the slope. The acceleration is less. Then here's the acceleration. It's less. So it starts to accelerate fast in the beginning, but then quickly reaches terminal velocity in which the acceleration would become 0. So I can kind of reason that out by just knowing that acceleration is the slope of the tangent line there. Which of the following acceleration time graphs depicts the acceleration of the bead? So again, it's starting with a big acceleration, and the acceleration is becoming less and less and less until the acceleration is becoming 0. And the acceleration is becoming 0 because it has now reached terminal velocity. All right, the last couple questions should be relatively easy because they are recent and they are about circuits. All right, determine the resistance of the heating coil in the coffee pot. I think this was on our last test. So we have, I'll say P equals IV. So we know the power is 450. We know the voltage is 120, so we can find I, and then we can plug that back in here. You can plug in your I value. We know this is 120, and you can calculate the R value. Referring to the circuit at the right, when the current flows from the battery, the amount of current is. So the current is going to come out of the battery like this. And when the current comes here, it is going to split. Some of the current's going to go this way, some is going to go this way. Where is most of the current going to go? In the path of least resistance. So most of the current is going to go the 8-way, but some of it's going to have to go the 24-way, and then it's going to meet together, and then it's all going to be together going through the 4 on its way back to the battery. So is it the same everywhere in the current? Definitely no. Is it greater in the 24 than the 8? No, because that has more resistance. Is it the same in the 24 and the 8? No, because it's going to take the path of least resistance. Is it greater in the 4 than in the 8? Yes, because all the current is now back together. All right, what is the power dissipated in the 4? Okay, we cannot do this question because we do not know the voltage of the battery. So we'll just cross it off. All right, the last two. You should know something about the electromotive force and terminal voltage. All right, let's try that again. All right, a battery with an EMF of 12. So let's draw that nice and big. So 12 volts. Has an internal resistance of 2. So a lot of times we show that by dotting this, so that internal resistance is like actually part of the battery. And it's connected in series with a 4 ohm resistor. What is the current in the 4? So even though this is an internal resistance of the battery, we still treat it like a normal resistor. So to find the current coming out of the battery, I'm just going to find the equivalent resistance. So there's 12, and so I have a 4 and a 2. They're in series, so the REQ is going to be 6. So I can now do the E equals IR, because this is the EMF. So this is 12. This is 6. So I now know that the current coming out of the battery is 2 amps. So now I'm just going to kind of talk to myself. So the current's going to come out of the battery. It's going to be 2 amps. It's going to come around here, and it's going to go through the 4. So that is 2 amps going through the 4. All right, the last question says, referring to the question above, what is the terminal voltage of the battery? So because I have internal resistance, I'm not really going to get a full 12 volts out of the battery. So what I'm going to get out of the battery, the voltage that I'm going to get out of the battery, is the theoretical voltage, the EMF, minus I times little r, which is the internal resistance. So this is 12. The current coming out of the battery is 2, but the internal resistance is 2. So I'm going to be losing 4 volts. So 12 minus 4 is going to give me 8, whoops, that's a V, 8 volts coming out of the battery. All right, I know there's spots in the videos that I meant to cut that I can't find, so I apologize about my mistakes, but I hope this kind of helped you walk through some of the things. And just know that if you can do these 40 things, you're in business and you're in good shape. I think the questions on the exam are easier than some of these. and shorter, meaning that you don't have to always pick up your calculator and number crunch. If you have any questions, please bring them to class on Monday and we will discuss them.